The broadcast is now starting. All attendees are in listen-only mode.
We'll start the presentation in about 5 minutes. Just want to give you a chance to make sure you can hear my voice, your speakers work. Good afternoon, everyone. Just going to go slow for a second just to get the numbers up of people just joining us. But welcome to our presentation on washdown water heating. This presentation will be about 30 minutes in length, and we'll have some time at the end to answer any questions. On the right-hand side, there is a box there that you can enter any questions you have, and I'll answer the questions at the end. And at the end, we'll leave some contact info for you should you have any further questions after. So my name's Mark Ducharme. I've been working at Spirax Sarco for 15 years. I'm the regional steam expert for Western Canada, and I work with engineers and processing facilities to improve the reliability, save energy and greenhouse gases, improve production processes, and improve food safety for their plants. So today I'm going to discuss the use of steam for hot water washdown. So in the agenda, we're going to go over hot water requirements for washdown, different methods of hot water heating, food safety and HACCP concerns, and how to reduce or eliminate any risks. So steam's used in many processes due to its high heat transfer capabilities, its ability to control temperature through pressure reduction, as well as the sterilization for products and services without using chemicals. So here's some of the industries that use steam. So milk, French fries, vegetable oils, canning, oats, cheese, meat products. So a lot of industries will use steam in their process, and they'll also use it for their washdown. So for the food processing facilities, sanitation is required. So hot water is an easy way of sanitizing surfaces, as you can spray it around. In the picture here, you can spray on all the food contact surfaces. You can clean the floors with it. But some important requirements for sanitation is the temperature that the water is at and the time required for sanitation to occur. So both of these are important. I also have a picture of a COP tank. So in that tank, you'll put a lot of the fittings from the food contact surfaces and sanitize the fittings outside of their normal installation. So hot water requirements. So two main requirements are the water quality. So the water needs to be potable and free from additives, and the temperature. So the temperature needs to be, depending on your industry, could be 170 or 190 F. In regards to water quality, so the Safe Food for Canadians Act has a couple important things on here. The water used for sanitation must be potable. So most facilities have these measurements in place to ensure they're using potable water in process and in sanitation. Some facilities do not place that same measure when considering steam. So you see in the regulations that any steam or ice that'll come into contact with the food must be made from water that is also potable. And depending on the temperature, I mean the application, the water temperature is always important, but depending on the application, sanitation may be at 170 F or up to 190 F. So you can see from this chart here, at 155 F, you can get burns within 1 second. So safety is important for also food safety, but it's also important for employee safety. So this should be considered when you're looking at different options for your washdown water heaters, to consider safety options. So methods of heating water. One method is direct injection. So this is where you're using steam as a gas and you're mixing it with the potable water to achieve a high temperature for sanitation. So direct injection steam will use all the energy from the steam and condensate, transferring it to the water. But it will also transfer the chemicals from the boiler feed water. So the boiler chemicals will transfer with the steam. And any debris found within the steam supply pipework can also transfer into the water. So these are some risks with direct injection. Steam pressure could fluctuate, which also could cause a variation in temperature. Reaction time could be slow to provide accurate temperature, as you're relying on a thermostatic element to expand and contract based on the temperature it's seeing at the nozzle. And I've seen instances where safety is a concern, where there was a malfunction or failure and steam was blowing out the hose, and there was a incident at facilities I've been to. So consideration when using steam and water mixing stations is the purity of the steam. So if it's contacting food contact surfaces, you will require clean steam, as plant steam will not be considered potable and could cause a hazard to the food safety program. This would come out in a HACCP analysis. Another type of water heater that can be used for washdown is direct fired heaters. So in this type of heater, there's you're using a gas-fired burner, and the flue gases, the exhaust, is heating up the water as it drips down across the flue gases. So you're gaining a lot of the energy from those flue gases that would typically go out of the building to the environment. But the result is you're adding unwanted gases to the water. So this could end up with a sulfur smell or taste, which I've seen in some facilities. And for this reason, it would not be considered potable water. So this shouldn't be used on food contact areas or in food processing. Another method that we would typically use is indirect water heaters. So the benefit here is you're separating the plant steam, so with all the boiler chemicals and any of the rust and scale found in the pipework is separated from the potable water on the process side. So this way you take away those risks, and you're still using potable water to contact your food contact surfaces. Some of the food safety guidelines that would be applicable. So definitely in Canada, we have Safe Food for Canadian regulations. If your company is supplying to US, you would have US FDA, and there's some international standards, the ISO 22000 for food safety management, and a couple other legislation here for European. In CFIA, on their guidelines, so the requirements for safe food for Canadians, they describe culinary steam as steam that'll be used when cleaning or sterilizing food contact surfaces. And they also say it should be free of boiler water treatment chemicals. So these 2 points make it pretty clear that you can't use a boiler with chemicals in it to be used on food contact surfaces. So for this reason, we would use clean steam generation to take out those chemicals if we were using direct injected steam in hose stations. So where do some of these contamination risks come from? So some of the risks are boiler chemicals, which I've talked about. In the pipework, there could be scale and corrosion, and also cross-contamination. So processes like CIP or it could be production processes where you have a steam heat exchanger. The condensate returning back to the feed tank and continuing on to the boiler could have some contamination in it that could transfer into your process. So there are contamination monitoring systems that you can install in condensate just to dump any contaminated condensate when it comes through. Or you can go to a system where you're keeping the plant steam separated from the potable water using indirect heater. In this slide here, you can also see a clean steam generator on the end. So this is another method of when you're going to direct steam injection, you can use that plant steam as the heat and energy source for a clean steam generator. So the clean steam generator would just have potable water without any chemicals. And from that point, all the piping would be stainless. And so you won't get the scale and corrosion in the pipework. And from there, you can use it for direct injection. So this is one method that you can use hose stations. Although it's taking away the food safety risk, it's not taking away the risk to employees if there is a failure. So for indirect water heating, here's just a picture, a P&ID of a classic open loop system where we have a steam to a hot water heat exchanger. This is typically what it would look like. You're going to have steam supply coming into a temperature control valve, going into a heat exchanger, and then a trap. And this trap is discharging up, which normally we wouldn't recommend. It would normally go gravity drain. This also could be a plate and frame heat exchanger. So similar, you're going to have plant steam coming in, temperature control valve, heat exchanger, trap, and then gravity drain. But you'll see on both these types of systems, you have a vacuum breaker. So with modulating control, it'll change the pressure available within the heat exchange, within the heat exchanger, and thus to the trap. So you could end up in the vacuum, and a vacuum breaker's purpose is to open up and set the system after the control valve to atmosphere. So how it does it is it opens up and air will fill the space. And once you have air filling the space, it'll allow the trap to gravity drain if it's sized properly for the static head from the heat exchanger out to the trap. So this allows air in, brings it to atmosphere, and the static head will be enough force to push the condensate through the trap. So some negative things in this is air and steam is an insulator. Air in general is an insulator. So you can see in this chart, if it was just the metal plate on the heat exchanger, you would have a slight loss in temperature across the plate. But if you have a film of air inside the steam side here, there's going to be a higher temperature drop. So the result is less heat available to heat your process. Here's some numbers just showing the thermal conductivity of air. It is really low compared to water and to metals. And steam with as little as 1% by volume of air can reduce the efficiency of that heat transfer by up to 50%. So we know this is an inefficient way of heating. As you're bringing air in, it's going to reduce the efficiency of your heat exchanger. You're going to use more steam to achieve your heat transfer. So this brings us to closed loop design. So a closed loop indirect heat source would be the more efficient way of heating, and it'll take away those risks of contamination with the piping and the boiler chemicals. And a bit of a video here. So you can see the cold water coming through. On the right-hand side, we have a bunch of temperature sensors. This is the steam side. So steam is going to start entering the heat exchanger, start heating this water. There's a recirc loop here to continually ensure our temperature control is at the point we want it to for sanitation. So by continually having feedback, there's always flow across the temperature sensor. And this may make sure we have accurate temperature control leaving out to the heat exchanger. To the process. So the process could be your wash down hoses. So now they're just water hoses. They're not a mixing hose. There's a number of safety features on here. If the temperature senses the water is too hot, there'll be a tempering valve here. So some of the cold water will bypass the heat exchanger and cool down the water that has come out too hot. So for some reason, there was a quick change in process and a spike in water there, temperature, will have this valve opening to temper that water and bring it back down to the set temperature. On the steam side, there is a high temperature ball valve. And the purpose of this is to ensure a tight shutoff. So should the control valve not have a tight shutoff on the steam, a ball valve will have a tighter seal and make sure that no steam will pass through. This will have a class 6 shutoff, so bubble tight shutoff. Typical steam valves will have a class 4 shutoff, so some slight bubbles can get through. So there's a couple levels of safety on here, as well as continuously monitoring the temperature of the water. With the closed loop design, the heat exchanger would be selected to operate under vacuum. And for that reason, we have a pump trap here. So this is using steam as the motive force. When the system's in vacuum, we don't have a vacuum breaker allowing air in. The pump uses the steam force to remove the condensate. So you can see condensate rising here, and the float in here is going to click open and saying, I need force. So it just opened up, it pushed steam into there, removed the condensate, and then it goes through a balancing process. So the pump trap allows this whole package to operate under vacuum without the introduction of air and to remove the condensate and still maintain tight temperature control. So the system size for no flash steam losses. So we designed the system to operate in vacuum. The pump trap will take care of the condensate. Because it operates at low temperatures, there's going to be low scaling within the heat exchanger. So we could have, well, I'll show you in a few slides, high pressure steam going in, but it's still coming out under vacuum. So accurate temperature control and data logging features. So if it's a requirement for the facility to log their sanitation temperature, there's that option in the control panel to data log and make sure for your HACCP program that you have accurate temperature for proper sanitation. And I've mentioned a few of the over temperature safety features. So vacuum condition, why is this useful? So here's a steam table. It's going from vacuum up to 30 PSI. The table would look pretty similar even if we went up to 150 PSI. The latent heat, the higher the pressure, so this is the energy used for heat transfer in the steam. The higher the pressure, the lower the energy, so the lower latent heat. And you can see as you go into vacuum, it continually increases. So at 20 inches of vacuum, we have around 1,000 BTUs per pound of steam. So that's the energy content of that steam. If we were operating at an atmospheric type of system where we're allowing air into it, you can see the energy difference. So there's a loss of efficiency by operating at vacuum, at atmosphere. So that's why it's important to, or that's why it's a benefit to design a system to operate in vacuum. So this picture is it's a close-up of one of those heat exchanger packages I showed earlier, with 100 psi steam going into this heat exchanger here. After the control valve, we're showing a pressure of 20 inches in vacuum, so over 20 inches of vacuum, although the system is supplied with 100 psi steam. And this is under a fairly high load. We have the control valve is open 65%, and we can still achieve vacuum. So we're at 20 inches there. So the point of this is to design your heat exchanger as efficient as possible. And results are, one other thing from the steam table I forgot to bring up is the condensate temperature. So 20 inches of vacuum, we have a condensate temperature of 160 F. So you're really pulling all that energy out. There's going to be no flash losses in the condensate return system. So considering the efficiency on selecting the heat exchanger, we had a Natural Gas Technology Center, an independent group that all the natural gas providers across the country work with. And they did a study of a system operating under vacuum, so plate and frame system versus a shell and tube. And we saw about a 7% efficiency gain. So some other benefits using plate and frame are maintainable. You can pull apart those plate packs and clean them, and you can expand them. You can add plates if you want to change a process and you're adding more host stations or increasing the processing side. And a long life cycle by operating under vacuum where the temperatures are quite cold. Different package options. So there's plate and frame like we've seen. There's we make packages as well with helical coil, also operating under vacuum. So you can see the pump trap in the background there. You'll still see the high limit shut off, the tempering valve. So all those safety features are on there. The picture on the right may be a little hard to see what's going on, but it's two packages stacked on top of each other. So there was a tight mechanical room, tight space required, and they still needed, these probably look like 50 GPM units. So they stack them up just to save space. Other things we've done is have a buffer tank on heat exchangers, either for high loads or where people just felt they wanted that extra buffer volume. In this application here, on the bottom left, we have effluent from process. So a lot of wastewater from the process is going into a sump. And we're actually using that hot water to preheat the cold water used for washdown. So the cold water is going through a liquid to liquid heat exchanger, and then it's going into a tank, and this tank is recirculating through the instantaneous heaters out to the hose stations and then back to the tank. So we have a continuous flow of hot water and ensuring that this loop is always at the temperature required for sanitation. So how to reduce or eliminate risks? So we want to select a system with accurate temperature control to ensure that we're meeting the proper sanitation for the facility. You want to select a heat transfer system with multiple levels of safety for employees. Also select a system that won't compromise food safety or taste, flavors. I guess those are other considerations at some plants. And select a system to maximize the energy efficiency. So in summary, we talked about the hose stations. You're washing down all the food contact surfaces. Water's an excellent source because it's potable. It can get into all those cracks and crevices under pressure. We discussed not adding chemicals to that water as it's going to deem it not potable. Temperature control will be important to make sure we're at the right temperature for sanitation and also for employee safety. We want to have those features that are going to shut that steam off to ensure that employees don't get burnt with steam going through the system. Yeah, other direct fired type heaters, they could affect taste, flavor, and deem the water not potable, so not recommended for wash down. And it would be a hazard, and that's where HACCP will come in. You want to identify those hazards and your critical control points. And discuss the heat exchangers with multiple safety levels and indirect heating to separate the potable water from the plant steam. And that's it for the end. It was just about half an hour, so I don't see any questions coming up. I'm not sure if anyone has any. I know there was a few submitted, so I'll go through some of the questions that were submitted. One was about calculating the washdown flow rates for various hose stations. We don't provide the hose stations, so we only provide heaters, but typically hose stations are about 5 GPM from what I've seen, and from when I've sized heat exchanger packages, it was typically used 5 GPM per hose station. And another question is, what are the advantages and concerns, or if any, or concerns of installing a steam and water mixing station over an instantaneous hot water system? There's a slight advantage of the direct injection on energy, but there's multiple disadvantages to the steam injection, and those are the safety, the risk to employees, and the risk for food safety and food contamination. So it's I guess I probably said a couple of times, the best method would be to use the indirect heating and design it as energy efficient as possible. So no flash losses and multiple levels of safety. Is the PowerPoint available to share? You know, I believe we're going to be putting the presentation on our website, so on our webinars, but I can share a PDF of the presentation to someone that asked. Let's see, this question's kind of cutting out. Oh, I think I know how to, I forgot how to make this question get bigger. Oh, okay, now I see it. I can scroll through. How do I, oh, there, so I pop it out. Okay, figure it out. Okay, I see more questions. Circulation, delta T, how do you calculate it? Calculating the losses on the loop, you would have to know the ambient temperature, whether these pipes are insulated or not, then the length, so the surface volume. So all that could be calculated to help figure out the delta T on that circulation loop. Is there a double-walled heat exchanger available where contamination is critical? Yeah, definitely double wall is available, both on plate and frame and shell and tube. And it's quite common to have it in washdown water, domestic hot water. People would want a double wall for that extra level of safety in the heat exchanger to ensure that the plant steam is not going to touch the potable water. In terms of the system design, it's not critical because on the steam side, we design it to operate under vacuum. So when it's under vacuum, if there was a crack in a plate, the potable water is going to flow towards the steam side because it's pulling a vacuum. So it's not going to affect the food safety, but it will affect the water going back to the boiler, and there would be concerns with that. So it's double wall will remove those concerns, but just checking your condensate pH will also indicate any potential areas where there's been a crack. And that looks like it for questions. Oh, I found another one popped up. Could you use a direct injection system in a hard plumbed warming application? So if you're just you're warming up something, so it can be done. So with direct injection, there's a couple of those things. The temperature control is not as accurate. So if temperature control is not critical, then you could inject directly there, as long as you're considering the noise, potential for water hammer, and lack of safety. That can be done, but if it's for food contact and warming food itself, then you would have to use clean steam. So I have a clean steam generator, so steam to steam generator, use that plant steam, create clean steam, and that clean steam can be directly injected in. It just won't be as tight of temperature control. And if any questions come up after, you can contact the three of us. So another question. Okay. Yeah, I'm not sure if I can answer this one right now. When we do circulation type, the startup time will be slower, question mark. This is because the delta T is smaller compared to the single pass type, but the delta P is bigger. Yeah, I'll probably contact that person directly just to make sure I understand that question. Try to figure out what they're asking in terms of. So typically we use plate and frame because there's higher heat transfer. The contact area is spread out across the plates, and so you get more efficiency in that type of heat exchanger. It kind of sounds like you're discussing maybe a double pass. Yeah, not sure. So I'll contact you directly. I'm just gonna write down your name so I don't lose it. Well, if that's it for questions, thank you for attending, and feel free to contact us if there's anything you want, if you want any further information. Have a great day.